The subject is the mineral elements that we need to grow plants. We studied this, we quantified the elements available in aquaponics, and we looked at the impact on the plant production, the lettuce production. We had to take lettuce as a study plant, you know, because it's impossible to study all the plants. So it's lettuce that we used, and we looked at the potential to improve the grow, improve the nutrients in the water. I will explain. So that's the plan of my introduction anyway. So a nice way that I like to introduce the necessity to make aquaponics. I don't know if you know this kind of this planet boundaries concept. I don't know if you never heard about that. So the idea is we have boundaries that for different aspects of the ecosystem. So we have climate change, biosphere integrity, which is linked with biodiversity. We have land system change. We have freshwater use, and we have biochemical flows, like for phosphorus and nitrogen. And you have different boundaries. When it's green, it's okay. We don't move too much. When it's yellow, we are in an uncertainty zone. But when it's red, we are beyond the safe boundaries. So we are in a high risk. And we can see that for all around the planet, the worst aspect at the moment are the biodiversity, that we have an extinct rate of species very high. So we are above the boundary, and the phosphorus and nitrogen cycle. So you know we have this huge problem of eutrophication all around the planet. So aquaponics is a good way to address these issues. Biodiversity, because we will reduce overfishing and the reduction of species in oceans. And of course, phosphorus and nitrogen will be recycled inside the system, and we try to not flush the phosphorus and nitrogen in the environment.
Question?
Yes, I like questions.
Because you're allowed in advance, I was wondering about freshwater use. I would expect it to be more drastic.
Yeah, me too. But it's for the whole world. So in some places it will be in the red, but they kind of make the average for the whole planet. That's the thing. So I'm already talking too much, but so if we take the example of conventional aquaculture, that could be a good solution for biodiversity saving, because you grow your own fish instead of fishing. But we have this issue that fish actually they don't have a good nutrient retention. So here are all the macro and micronutrients we need to grow plants. Okay, and if we look at that we need for plants, but that is found in the fish feed, actually. Yeah. That is found in the fish feed. But if we look at it, we know that the fish they don't assimilate everything. So most of the things, like 30 to 80% of these nutrients, are released in the environment. So we have eutrophication problem. So aquaponics want to address this. So now we come to aquaponics. So I like to have a simple drawing to show what is aquaponics. So if you go out of your backyard aquaponics, if you want to, like the video we saw Monday, if you want to do it as the small commercial scale, this is the principle that most of the people use. So it's a one loop, it's a one circle water. So you have the fish tank, mechanical filtration, biofiltration, sump. So that could be a recirculating aquaculture system, and just connect hydroponic beds, and you loop in one circle. Okay. So I mostly studied this kind of system and look how we can improve this. So, for example, first thing we have to look at it. It's all in this water loop. the macro elements and the micro elements we need to grow the plant. So we have to, I looked at all these nutrients, okay? Here you can see in red, it's the hydroponic standard, the concentration in the hydroponic solution for lettuce. And in blue, it's what you found in literature, like it's already 10-year-old, even more. It's the Rakosi literature. It's the best literature I found when I started my thesis. So you can see that it's in blue and it's very far from the target, okay? Especially phosphorus is very low, potassium, calcium, okay? So that's might be an issue. Another issue is that actually we use mechanical filtration, and as soon as you use this, you remove the sludge out of the system, and so many nutrients are contained in the sludge, especially phosphorus is mainly released in undissolved form by fish, so you remove it directly out of the system, but we just saw that phosphorus was already really low compared to hydroponics. So that was the main finding, the weakness of a one-loop system we identified at the beginning of the thesis. I found some research teams. I defined objective for my thesis. So one of the first objectives it was to look at the performance of a one-loop system. So look at the environmental impacts, so energy and water consumption, mineral element accumulation. So all the mineral, look at it, what is accumulating, what are the mass balances of this element. Then I focus on the plant growth. Is the lettuce, so here we took lettuce, is lettuce productivity the same in aquaponics and hydroponics? Is it different? How can we, what can we see if we, for example, increase the nutrients in solution? So I will show the result. And then to address this issue of the sludge, so using sludge digestion to recover the nutrients and put it back in the system. So that was the three main goals. So first objective, then the performance of one loop. So we have in our lab in Jean Blou, we have what we call the path box for plant and fish farming box, which is a one loop system. You can see here it's very simple. Fish tank. It's the same principle as I just showed. So fish tank. Mechanical filtration, sump, pump, biofilter, beds. So the beds are, the hydroponic beds are in the greenhouse on the top, the fish are here, and the water go up in the greenhouse, come back in the fish tank in a one loop. Okay, so we studied this system for 1 season. Now it's running for 4 seasons, but we focused I focused one paper for 1 season. We made a lot of measurements. So about the water consumption, we had in average on the season, so from April to September, 3.6 daily water exchange, which means 243 liters per kilo of feed added. And you can see that actually we had not a constant water exchange. It varied during the season. If we compare this water consumption to other systems, so here is you can see different kind of aquaculture. Yes?
Are you giving some supplement of nutrients to your system also, or it's just from the...
Okay, we decided to not add any nutrients. We just use tap water. I will show 1 to 2 slides later. So the thing is, we just use fish feed as nutrient input and tap water.
Okay,
the water, just the water.
Water from the fish tank, is it the same level of the hydroponic solution for lettuce, or it's missing some nutrients?
I will show it just in a moment.
For
Just keep in mind your question and you see if I reply.
And this is only for tilapia RAS systems here?
No, it's classification of aquaculture. So you have flow-through system. You use more than 50,000 liters per kilo of feed added. Then you have, like they call reuse aquaculture system when it's 1,000 to 50,000. So what we call RAS, you are in recirculating aquaculture system, you use 100 to 1,000 liter per kilo feed added. We were in this range, in the lower part of this range, but there is already innovative, what they call innovative RAS, so the RAS that use denitrification basically, that are under 100 liters per kilo feed added. So we were not that good actually. We were okay, but not that good. Normally we would expect with aquaponics to use less water than in a recirculating aquaculture system. So there were something not that perfect on that side. About the energy consumption, that was pretty simple. So we can see that almost 60% was used just to warm the water. We used tilapia, and we just used electric heaters, like aquarium heaters. And so you can see that it's 60% of the energy. And then second big point is the pumping. Of course, also pumping water in the greenhouse and going back. Maybe it's, so there are 2 points. There are using tropical fish in cold climate. Is it wise regarding energy consumption? And pumping the water up in the greenhouse, is it the best solution? So we use this amount of energy per month, 1,000 kilowatt hours. Yes?
This is only for this season from April to September, not the whole year average.
No.
Why? Water heating? It was some.
We wanted 25 degrees for the water.
Not a range, just 25.
Yeah, but you know, in April in Belgium it's cold.
Okay. Not July.
Yeah.
September.
Yeah, it's an average on all the season.
So how much is the production target for fish and plants in your experiment?
How much was the production?
Yeah.
We didn't get any target. We just looked what we could produce. We respected the ratio fish to plant that Rakosi advised. So which is like 50 gram per square meter of 50 gram of daily feed input per square meter of hydroponic beds. I calculated the energy needed to produce 1 kilo of vegetables and 1 kilo of fish, and the water used to produce 1 kilo vegetable and water fish. The pavbook is in blue, so you can see that for vegetables we use more energy that another study about one loop system, and then in data from hydroponics greenhouse. For the fish production, we were quite in the average, but some recirculating aquaculture systems are very low here. I found some data. For vegetables and water use, we used more than other publication to give an idea, and for the energy it was equivalent. But this is very tricky thing because it's difficult to compare that stuff. It's just to give an idea, okay? So regarding now the mineral elements accumulation in solution, what we saw, it's actually what controlled the EC the most was just nitrates and calcium in our case, which means that the other nutrients didn't accumulate fast, didn't accumulate really quickly. So do you have an idea why I put this dotted line here? Can someone tell me? Why did I put this line here? What is the link between these two graphs?
To maintain the pH?
No, there is no pH on these graphs.
It's the stability, it's the plateau.
Yes.
It's
What
when you
creates the
exchange
stability?
this, you have the same constant level of nutrients.
Yes.
But I guess it much depends on the uptake by your plants.
Yes.
It's a steady state condition of electrical conductivity
Yeah.
caused by water exchange rates.
Exactly. So we had a staggered production, so we can assume that the nutrient uptake by plant was constant, okay? And we can see that at a certain threshold of water exchange, we actually control the EC. So what does it mean? It means that Actually, the nutrient input was equal to the nutrient output in the system. So actually, we lost all our nutrients just by water exchange.
How did it affect pH?
pH was dropping, but because of high water exchange, we had tap water, so the water was rich in nutrients and alkaline, with a high alkalinity, so it controlled the pH. So if we look now at the concentration of the nutrients, so it's your question. So you can see here it's a bit better than Rakosi, but we are still very low. We were very low in potassium and phosphorus compared to, again, the hydroponic standard.
This is the hydroponic solution recommended for lettuce?
Yes.
Or in general?
For lettuce. It's normally the solution they used yesterday in the greenhouse. It's NFT standards. Now if we look at the mass balances, so the only two inputs of elements were from tap water and feed, and you can see that actually most of the calcium, magnesium, sulfur, and even sodium, that is interesting, were inputted from tap water. An interesting thing is we can already look here if the ratio between elements are balanced compared to hydroponic solution. So I made the ratio to n, and what we could see, it's already in the PAF box, we have a deficit in potassium and iron since the beginning, because the feed doesn't input this in enough proportion to nitrogen. Okay, so in such system you will always have an issue on potassium and iron if you assume that all the nutrients are ending up in the water. Now, if we look at the mass balances output, that was quite disappointing result. That we have to be careful with this result, but what we can see is most of the nutrients inputted were lost, like more than 50%, which means that the plant actually in our system didn't uptake that much. It's around 1 or 2%.
So it's all in the sludge? Where does it go?
So the sludge is in black here. So we can see that phosphorus, nitrogen, and all micronutrients were accumulating mostly in sludge. Okay, that's the main information. After some in solution, the one that were actually inputted by tap water were mostly in solution. But the rest were lost. We don't know exactly where, but mostly I think by water exchange. I just show you that with.
In the solution, why do you say they're lost? They're still in the system, right?
No, they are out of the system. So in the system, what we analyzed, I analyzed solution, the plants, the fish, and the sludge. I analyzed the nutrients, so I know the mass of all these elements. I know the mass of feed I inputted, so I know what kind of nutrients I don't find in this. I lost in all these things. Do you understand?
You mean that the organism used them?
It's a mass balances. So you have for nitrogen. During the whole season, I inputted 1 kilo of nitrogen. Okay, I looked how many kilo of basil I produced and how many grams of nitrogen I had in basil, in all my lettuce, in all my fish, and in all my sludge.
So where is it lost?
So it means that
Where is it lost? What do you think?
For nitrogen, can be denitrification.
Hmm?
Denitrification, nitrogen.
Yeah, to the atmosphere.
Yeah, but you forget something. This
Water.
we had a water exchange of at the end 5%, and you can see that it controlled the EC, which means that actually when you just throw your water out of the system, you throw your nutrients.
But you don't throw out water.
Yes,
water lost?
You have a water exchange, so it means that you release water in the environment.
Your 3% is water that you send to the drainage. It's not evaporation.
Okay, it's both. It's both. The evaporation we can estimate it, and it will be less than 1%.
So And why do you need, so I missed something, why do you need to send water to the drainage? Why do you need to get rid of water?
So we did it for cleaning the filters and when we remove the sludge. And also sometimes we removed some water to control the pH. So we just threw water at some point.
Okay.
Why do you say that you assume it was lost in the water, and why didn't you calculate it? Because you know how much water you throw away, you know the composition of your water, so why didn't you calculate it?
No, I didn't measure exactly the water we throw away. I measured the water we inputted because it's difficult to measure the water you throw away. And there are other parts of the system that I didn't measure. For example, the tank walls, the biofilm in the biofilter. So there are nutrients there also.
And did you measure your basil lettuce, or is it based on literature data?
No, it's all analyzed on site.
And what about the percentage of error for the analysis?
Yeah, there is. I cannot exactly tell.
Because with ACK method, for example, it's between 7% to 15%.
No, it's very low. Mostly it was analyzed with ICP, which is less than 3% error. No, there are definitely you should not see as the true. There is error on everything, but you can see the main phenomenon that's happening. Regarding the plant production, the plant grow. So in this PAF box, now it's running for 4 years. We had good grow actually, without adding anything. We had a good grow. We had no deficiency. We just sprayed iron just to make sure there is no, to prevent deficiency, iron deficiency. But we didn't really do it as a regular basis. And now for 4 years, it's producing good, nice vegetables. We tried other stuff like even beans. It worked. Cucumber is working very well. So it's working. But we cannot really say, okay, it's better or similar to hydroponics. We need to go further, yeah?
So was it foliar spray of iron, or you put it in the nutrient solution?
No, we didn't add anything in the nutrient solution to really see the dynamics. So we sprayed iron sulfate.
Iron sulfate.
Yeah, it's from another publication. We wanted to compare the growth of lettuce in controlled condition to really see if we use aquaponic solution, hydroponic solution, and we tried a third treatment, which we called RAS water complemented. We wanted to see the growth in these two treatments. So aquaponics, we created the concentration we found in literature from Rakosi. Okay, so what we did is we had a recirculating system. Tilapia aquaculture recirculating system. We took this water, we actually had to dilute it to get this value, and we added some nutrients to be exactly at the value of the literature. We made an hydroponic solution. This is easy. You take rainwater and you add the nutrients. And we made what we call a recirculating aquaculture complemented water. So the objective is to run the system in the same condition as hydroponics, so same pH condition and same nutrients concentration. So you can see here and here we have exactly the same profile of nutrients. So in green, that was the profile we had in the recirculating water, and in red, that was the nutrients we added to have the same concentration. Okay? So we have 3 different treatments, and we looked at the production. So just
actually taken from a RAS unit?
Yes, tilapia RAS unit that we have on site.
So your own unit.
Yes. So the value of this is common value of what we can find. You can see that we had to add a lot of phosphorus, for example. Potassium nitrate actually. So in hydroponics, you look at the ratio between nutrients. So we looked in during our experiment. We looked at the ratio that are here. So ammonium to nitrate, calcium to potassium, calcium to phosphorus, calcium to magnesium. So you can see that our hydroponic is in red and complemented is in blue. You can see that they were quite the same. Okay, we can say the plants were growing in the same nutrients conditions. Okay, you agree with that? But the aquaponic ones it was in green, and you can see it was really different. What we got as a result, that was very interesting. So we did one repetition. So we did it 2 times. We had here are the statistics here, but this is summarized here. It's much easier to understand. What does it give in 2 experiments? Aquaponics and hydroponics, we got exactly the same leaves, the head mass, okay, statistically the same. And in the complemented, we had 39% increase in both cases. Okay, that was really interesting result. That was quite impressive. I will discuss later how we can interpret this. But what we found also is in the treatment with aquaculture water, so aquaponics, and this one, the roots mass was higher. The roots of the plants were higher. So this is published. You can get these papers. You can go deeply into it and cite it, please. So what we found that for energy and water that was not that amazing. We had a quite low nutrient level in the solution, but we actually had a growth similar to hydroponics. But we know also that we have another issue is the sludge is going out of the system, but it's full of nutrients. So we should reduce the nutrients in this sludge to, one, avoid to discharge to the environment, because we saw that actually we discharge a lot with sludge and water exchange, even in a one-loop system. And second, if we increase the nutrients, I just show you that you can increase the yield. So it's really interesting to do that. So the idea is we have the sludge, we digest it, we find a way to recover the nutrients, put them in solution, and put them back in the system. Okay, and then maybe you have to modify the system. Maybe not a one loop. This is why I put red arrow and everything. But I will go deeper into this just later. So just now we focused on sludge digestion. So to do it very low tech and simple on aquaponic side, you have 2 solutions. You do aerobic digestion or anaerobic digestion. We tested both and we compared. So here is the reactor, the bioreactor we used, very, very low tech actually. So the anaerobic one is just actually a bucket where you put the sludge and you let it settle in the bottom, and it gets anaerobic. It's like imitating what happens in the nature at the bottom of lakes, ponds. Okay, and we just mix it every time we add fresh sludge. The aerobic one is just you blow air, and you have like a moving bed reactor. It's just like all the time mix it, and there is air in there. Okay, and of course we want them at the same temperature. So this is why we put them in the same water bath. We did this in 3 universities from the coast. So we did a first experiment in Zurich. Then we had another experiment in collaboration with Wageningen and Simon. So we pulled the result from 3 sites. So it's 3 different recirculating aquaculture systems, 3 different sludge, but we put them together to have a nice view of what's happening. And what happened, if we look at, there are 2 things in sludge reduction. You we can look at what we call the reduction potential. So it's the solids, so really the amount of solids that will be disappearing, okay? This is what we call TS, total solids, and the COD, the chemical oxygen demand. So how this oxygen demand will be reduced, okay? This is the reduction, and then you can look at the mineralization, so nutrients you can get out of the sludge. So here it's the reduction. So what you can see, it's actually in all our trials, aerobic and anaerobic were the same. We had statistically the same performances, for both close to 50% reduction. So now the mineralization, so the nutrients we can recover out of the sludge, okay? So here it was also quite similar. Only the difference was for nitrogen, and we got some accumulation of nitrogen in aerobic treatments. Okay, it's an average. You can see that there are a big standard error, but that was the trend. Okay. So we wanted to go further because the results were not not enough interesting. We want to recover more nutrients than less than 10% of the nutrients inside the sludge. So we looked at the literature and we found that this kind of reactor are very promising. So it's a upflow anaerobic sludge blanket reactor. So it's an anaerobic reactor, and how it works, it's actually you have a recirculating flow into it. So the pipes, you have the pump here. So you have a constant upflow. Actually, it's in that way. So the pump push the water here, and you have, like we call it a sludge blanket. So the sludge is in the bottom and it's slowly mixing, and then it goes up there and come back again. Okay, and this kind of bioreactor, they produce biogas also. So you could recover methane to produce energy. Okay, this is an EGSB. So we found that you definitely need to treat the effluent of USB. So we found that EGSB, expanded granular sludge blanket will be good for do the post treatment of USB effluents. So we test the same value, so sludge reduction and sludge mineralization. Just to show here, we actually had a very interesting thing happening. One of the USB reactor went become acidic, so the pH dropped under 6 in one reactors. And I just show you that because this reactor worked in a different way, and that was very interesting. So we can see here for the reduction, so we look at here at total solids, COD, and also we look at cellulose reduction, hemicellulose. And what we can see, it's actually the one that went acidic here at a very low performance for reduction. Okay, and and it was statistically different in this case and in this case. The other one, so in red is the USB that are at the good pH, and we compare to what we call our control. It's our anaerobic and aerobic simple reactor. They are our control, and we can see that we are not that far from them. So even aerobic seems to be better for COD removal. So now at the nutrients mineralization, here we can see that actually for all these macro elements, the acidic USB were definitely the best and statistically the best, okay? Except for nitrogen. For nitrogen, it was not that good. The USB was the best. So that gave interesting information. Are you okay with this? Is it?
Do you have any idea why the pH dropped in this one
reactor? It's actually the fermentation process stopped, and you have an increase of volatile fatty acid production. So it's at the first stage of fermentation, so anaerobic digestion. You have a production of volatile fatty acids, which are acids, so they lower the pH. And at some point, the bacteria that does the next step didn't do their job, so it was stopped at this phase. So it explained actually that we had very low sludge reduction because actually the digestion stopped. They were like a crash of the process. I don't know, Simon, if you can maybe.
Well explained.
Yeah.
Crash. Yeah.
It's
How do you control the flow rate? The flow rates, and maybe you went too high with the flow rate, so the bacteria growing there couldn't keep up with the flow rate in your reactor.
No, we use the flow rate that is the same, and it's the flow rate from the literature, so it's a very low flow. But yeah, it's quite strange because I actually didn't say it, but in ULG, in my university, we had one set, and at Simon University there are two sets, and one of the two sets become acidic. So it's something we didn't control. We don't control properly. But we also you can prevent it. If you see that the pH drops too much, you should. But we put sodium carbonate to higher it. But you should manage that the pH doesn't start to drop. You should do it before it starts to drop. When it starts to drop, it's already too late because we tried and Simon tried, and he couldn't get the pH up again. It was like the process crashed. So yeah. So this is something important for the future. To summarize, when you have a good sludge reduction, you have nitrogen mineralization. So in the USB with the high pH, we had good nitrogen production. But for the other micronutrients, we needed a low pH to have good mineralization, and that can be explained by the fact that actually in sludge, these elements are not trapped in the organic matter, but more are present as precipitated minerals like struvite or calcium phosphate. So these things, to mineralize them, you just need to lower the pH. Okay. We look also at the concentration of nutrients in the effluent, because we want to take this effluent to put them back in the hydroponic solution. Okay, so we looked here. I compared again to the hydroponic targets, which is in blue now, and you can see that we were quite better. For example, for phosphorus, so it's in all. Here it's the 3 USB we tested. You can see we were quite close to the target. Potassium was still bad, but for the others it was not too bad, except for nitrate that was absent. Of course, in anaerobic condition, you remove the nitrate, and we had a lot of ammonium over the target. For micronutrients, it was a bit disappointing. So very low compared to the standards. So now I'm going to finish. I don't know if I have already been too long, but for the perspective for future, all these results. First, for this amazing growth in complemented aquaculture solution, we have two hypotheses that may explain the better growth in fish water. There are two factors that might be able to promote the growth and increase this root mass. This is the rhizospheres, the microorganism present in the water that might promote the growth, and the dissolved organic matter. So, like we know that, for example, that humic acids will promote the growth, and these molecules we need to focus on this. But if you can prove that these molecules are in the fish water, some are really known to improve the growth. So and also they can also directly feed the plant, like some amino acids. Maybe the plant can uptake some amino acids. So here we are really at the at the limit of the knowledge, and we need more fundamental research about this. And there is now a PhD student carrying on this kind of research in our lab. So regarding the sludge digestion, what we found out is we should do it in a two-step. So because we cannot get at the same time sludge reduction and mineralization, so we need two steps. One first step to do the reduction. So we suggest in a USB with IPH to get so organic reduction and nitrogen mineralization and biogas production also we could do it. And then another stage which is low pH for the other micro and micronutrients mineralization. And maybe still a post-treatment, so it's complicated a bit the thing, but this is what we found.
And then you would get like sludge that can actually be fed back into the solution?
Not the sludge, the effluent, so water full of nutrients, dissolved nutrients. That's the idea, of course. The sludge, we want to reduce it in the first step. We want the solids and the organic matter to disappear, to live as biogas basically, or be dissolved as dissolved nutrients.
Yeah.
Okay. And so, if we want to integrate all these findings, we suggest to use a more decoupled approach. So it will be more like a multi-trophic system. So you have different loops that you connect together, but maybe not like a simple one loop where you recirculate all the flow through, but you just send the water to different parts. So, for example, the sludge goes in a mineralization plant, and then the effluent goes to the hydroponic plant, and then you can also send directly the water from the aquaculture in the hydroponics. So something more decoupled. But I will let Simon explain because he really focused this thesis on this. And just to finish, also maybe we could go on a hybrid decouplet. So keep the idea of a couplet system, but with the sludge and maybe the extra water, have another decouplet hydroponic. So it will be an hybrid things. So why hybrid? Because we still need to control the nitrates here. So it's still good to have maybe plants in the fish loop, but we saw that if we just do it like that, we lose a lot of nutrients. So it's also important to treat other effluent like the sludge and maybe all the water. I show you that in our system, I exchange 5% a day and I lost all the nutrients. So all the water I remove even from this system, we should use it even to grow plants. So that's the theory, and that's it. So thank you.